Good morning, good afternoon, and good evening, depending on where in the world you're joining us from. Welcome to our expert webinar, Scaling Graph Learning for Your Enterprise, brought to you by our friends at Kumo AI and Snowflake. I'm Brian Mink, co-founder and president of Data Science Connect, the world's largest data and AI community. Today, we're excited to welcome hundreds of attendees from all over the world to discuss how to scale graph learning for your enterprise using Kumo and Snowflake. Relational databases like Snowflake house much of the world's critical data, but building predictive models from this data can be slow and error-prone. Hours of feature engineering to join and aggregate models into a single table ends with suboptimal models. A new method, Relational Deep Learning, RDL, eliminates this bottleneck by treating the Snowflake database as temporal, heterogeneous graphs where rows are nodes and primary foreign key relationships form edges. Today, we'll take a deep dive into all this and more with Hema Raghavan, Vice President of Engineering and co-founder of Kumo AI. Hema is responsible for developing the AI technology to help Kumo users build better predictive models, and previously was Senior Director of Engineering at LinkedIn, where she led a globally distributed diverse team that built AI and ML solutions for fueling LinkedIn's growth, including people you may know and the company's air traffic controller AI that govern member communications. Before we begin, a few housekeeping items. First, to make this feel a little more in person, we suggest you add a photo to your profile and include your bio, LinkedIn profile, and other information you may want your fellow attendees to see. Next, please take advantage of the Q&A and chat features throughout the webinar. Hema will be answering questions throughout, so be sure to upvote the questions you'd like her to address. If you're wondering where your organization stands compared to others on your scalable graph journey, check out the poll questions in the right sidebar. And finally, to learn more about how to scale graph for your enterprise, check out the calls to action below throughout the webinar from our sponsors, Kumo AI and Snowflake. Now, without further ado, I'll hand things over to Hema. Welcome, Hema.
Thank you. Just give me a moment and I will just get started. Thank you, Data Science Connect, for having me here. I'm Hema Raghavan, and I am a co-founder and VP of Engineering at Kumo AI. And at Kumo, what we're doing is taking a lot of the lessons learned from the founding team. The founding team comes from Airbnb, Pinterest, and LinkedIn. I myself was at LinkedIn for several years before forming Kumo, and my co-founders are Yuri Leskovic, who was chief scientist at Pinterest. He's also a professor at Stanford, and many of you know him from the graph learning work that is that he has pioneered. And the CEO of the company is Vanya Josifovsky, who was the CTO of Airbnb and Pinterest. The founding team is also the team behind various open source libraries like PyTorch Geometric, PyTorch Frame, RelBench, and so on. At Kumo, all of us came to Kumo with similar, experiences in building data science teams. But I'm going to start with the motivation, which was my own personal journey. And I was, for the longest time, I started my, AI and machine learning career in the field of information retrieval. And some of the first systems that I built were question answering systems. And this is what question answering systems look like circa 2003. So I'm dating myself when I say this. But if you had to build a system that says, what year did Marco Polo, travel to Asia, or systems that could answer those kind of questions, you would actually have to understand the underlying structure of text. So you would write these big document processing systems that could do tokenization, part of speech tagging, named entity recognition, and so on. And you would glue it all together so that when a question was asked, you could parse the question, and then you could do pattern matching between patterns, that is actually lexical and semantic patterns between the question and the answer. So each system took multiple years to win and handcrafted features. And when I talk about features, I mean all of those part of speech tags and named entity recognizers. It used to take multiple years to build winning systems. And then over the course of the 20 years, we had, more data-driven systems. We had an entire GPU revolution that happened that we can now actually have algorithms just reading raw text, right? So the algorithms find those underlying patterns, and it was that transformer revolution, the paper, the attention is all you need paper that really changed things because all you needed was to give systems large amounts of text, and then those intermediate layers in a neural network were learning the patterns that we used to human engineer, right? So uh, in the 20 years that the text processing field made these leaps and bounds, I had worked on text systems, but I also worked on ads, recommender systems, and so on. And 2014 is when I came to LinkedIn. And what I was, at least what I felt at that time when I came to LinkedIn was there was this, you know, amazing revolution that was happening in text, but a lot of our production ML system was as, complex as classical QA systems. And data science really takes many steps. I hope some of you will go to the poll and answer some of the questions. But data science for my team used to take, we used to spend some time in problem ideation and sponsorship, but we spent a lot of time in data prep, feature engineering, model development, and so on. So it would take a quarter to build a model. And really, as a data scientist, what you wanted to do was speed up that cycle and spend as much time uh, as you could on problem formulation or on model development. But we were spending a lot of time in those in-between spaces. And even after you brought those models to production, these systems were, a nightmare to uh, sustain in production, right? So my favorite story to narrate is always where, we had this big ecosystem of data ETLing from front end to back end, building, plumbing the ML system, and then further, powering recommendations. And then once a front end engineer just turned off a tracking event, and that blew up a bunch of models. It took us 3 months to debug that. So on the on-call load, the maintenance load of these systems that are, that are an aggregation of pipelines is just a pain to maintain. So we were looking at this generative AI revolution, and we were just saying, things have gotten so much more easier there. But there's this whole world of predictive AI, the use cases on the left-hand side in this chart. Uh, Personalization, next best action, churn, lifetime value, they all have a common property that you're working on private data, that is your company data, and you want to predict an action based on historic trends and behaviors. And can we bring the transformer, revolution to this kind of workload? And that's what really motivated Kumo, right? And And really, if you look at the kind of data that predictive ML works on, it's typically the, you know, uh, relational data that it works on, right? So, think of tabular data, data that is connected by primary key and foreign key, right? And this spans use cases that go from commerce, finance, social media, and so on and so forth. So even though Pinterest and LinkedIn, where we work, were social media companies, you can actually think of graphs as everywhere because if you start thinking of, all of your relational data as graphs, then um, we can start thinking of some of the technology that we were building for our social media companies and bring them to commerce, finance, and all of these relational workloads. And that's really the key, hypothesis that got us to form Kumo. So to go a little bit deeper into, where are we spending the time when we do predictions and relational data? Um, let's take a simple three-table example. So, and I'll keep coming back to this example. It's actually from the H&M Kaggle data set. There are three tables. There's a transactions table, which has all of the transactions that customers have done on products, okay, or articles. And if you had to, you know, uh, predict churn, so let's say you have a user and you want to determine the label of churn or not, what you would typically do is write some SQL that looks at all the past transactions. And then you may say, hey, this user had a transaction in April, but none in May. So she's churned in May, but then she's back again in June. So to create your label data set for ML, that's one place where you're spending a lot of time writing code to process. And then once you've created your label data set, you need to be able to map features to align with the time of that data. So I hope this really, rings or strikes a chord with all of our data scientists in the room, because we call it time travel SQL that you're writing. And once you do that, for every feature, and especially every transactional feature, you start writing SQL code that looks like this. You start playing around with sum of transactions in the feature generation period. Someone may say, hey, it's not 30 days, but it's 90-day transactions, which are great for our data. Someone may say average transactions is better. So you're writing a lot of code, to generate data in these to prevent information leakage, right? So that's the key problem that you're trying to solve from a data science perspective. And then we started asking ourselves, why did we all get into data science, right? Was it to write the tons and tons of SQL that does, time travel and training data prep and so on? And really, many of us got into data science so that we could architect models, train and improve the models, but really find those areas where models can impact the business and impact the business, right? So the amazing part of running a DS team or an ML team has always been on the impact to the business and how well is uh, how well we can directly impact the business. Um, I saw the question from Chirag at Compass. I will answer it later. So thank you, Chirag. When I come to the demo and the later part of the product, we'll talk about how we can scale. So we started asking ourselves, is there light at the end of the tunnel? And we said, can we actually have transformers that capture the meaning of data, but not necessarily textual data, the data that we have in our relational data warehouses? And this field that Kumo and Stanford and collaborators that we have at Max Planck, Yale, and UIUC, uh, we created a field called Relational Deep Learning. We put a bunch of artifacts out in the open source. They don't scale to the extent that Kumo has built out, which is more production grade. But you can actually play around with the concepts and the idea in the open source in RelBench, PyG, and PyTorch data frame. So coming to the Kumo platform itself, what we decided was we wanted to solve this problem of making data science easy, but there are really like, how do we make this work, right? So to understand what happens behind Kumo, and you are all data scientists, so before I go to the demo, I thought I have to give you the inside technical meat of what we do. You have to understand two ideas. One is that all predictive AI tasks can be described in a domain-specific language. And that is one key innovation of Kumo. And the second one is that all predictive AI tasks on this relational or structured data can be generalized to a graph transformer problem. When you put 1 and 2 together, we get a data set we're able to create a data platform that makes you more performant, both from a speed of iteration as well as model accuracy. So let's go to that first insight, right? So one of the Kumo's key innovations is this predictive query language. On the right-hand side, you see our TQL framework. And here you have, think of it like SQL with a predict clause. On the predict clause, you have an operator, and the operator allows for Boolean expressions, sum, average, a whole bunch of operators. And that's really the label that you're trying to generate. The for each says what entity in your data warehouse you're generating your predictions for. And the where clause lets you do, filtering. And we all, as data scientists, know that sometimes we think that these windows, the past windows, right? Like in this case, we're predicting the sum of transaction price is basically a quantity. So it's a regression problem. And it's saying what is the lifetime value over the next 30 days of this user. And the where clause is saying just look back in the previous 30 days to make this estimate because, and think of it, you can express so many different variants of your LTV query itself that way. But this language is so rich, we can generalize it to forecasting problems, that's the bottom left. And you can also do recommender system or ranking problems using this. So go to our docs, you'll get a flavor for this language. Now, given this language, the second insight is that we can bring that, that all that hairiness that we had for the time travel, we can distill it down to one schema of a training table. And really, whether you have a classification problem, a regression problem, a forecasting problem, it's really three columns with some distinction in the label format. So the label may be Boolean, or it may be a quantity or a set. But if you have that flexibility in the schema, we can actually design a language that goes from the predictive query to automatic table creation. Suddenly you can eliminate a lot of those feature engineering workflows that we had. So that's one idea behind Kumo. But you may say, hey, wait a second, that's just the labels. There's just three columns there. What happened to all my features, right? So that's where the graph comes in. And that's the next idea. So we'll combine these two ideas in just a moment. But the second idea is you have the structured data. So you have your user table, your product table, you have your transactions table. And relational deep learning takes these three tables and then joins them together to make a graph. And this graph is basically constructed in the following way. Each table is a node type, each row is a node, and each primary key, foreign key defines an edge. Columns are node attributes, and time is a first-class citizen on this edge. So this is where the core graph is. So you have this predictive query layer, and you have this graph that we are creating at the bottom. When you join that training table to this graph, what you get is this very rich representation that is under the hood of Kumo. Okay, so you remember we had this user at the top left of my slide here. She churns in May, but she's active in June. But then you visualize this entire thing as a graph. And what are you doing when you do feature engineering? You're looking at features across transactions, but sometimes you're also looking at the fact that, hey, she bought a red shoe, but she's never bought those goggles. And people who buy the red shoes tend to buy the goggles as well, right? So those are the kinds of features that methods like collaborative filtering and all try to capture. But can the underlying GNN capture these features? Can the underlying GNN actually capture the fact that the user is clicking on a lot of red items and maybe have an affinity to red? And the answer is yes. And that's where this whole relational deep learning to graph and graph neural networks come together. Okay. And really, on this rich representation of this graph that we have, we, we have this predictive query language. We, what kind of problems can it solve? And it actually, we find that all machine learning problems eventually can be reduced to either node prediction or link prediction problems. And either their classification or node prediction or regression problems, or likewise classification and regression on link problems, right? So once you see all of these patterns together, you can actually create a very generalizable platform. And we put it all together, and that's really what is happening under the hood in Kumo. Sometimes people will ask us, can you actually bring in uh, you know, the richness that we have? Like many times you are learning embeddings about a user. You might have embeddings about uh, item from that learned from images about that item and so on. And yes, all of those are pretty much node features, the graph transformer. So I'll show you in a moment where those would come in. And this is the idea behind Como. So if you think of where ML on images went, we went from hand engineering features to a universe where we can learn embeddings optimally, where pixel neighborhood was what informed what a pixel was about. Likewise, graph neighborhood is what defines what a node or an edge is about, right? And that's the powerful idea that we can actually generalize to a whole bunch of ML problems, ranging from growth problems to recommendation to fraud, forecasting, and so on. So with that, I'll just jump straight into a demo, and that will make it clearer as to what the platform is, and then I'll come back to the slides. Kumo has one of the many deployment models that Kumo has is on Snowflake. And you can actually go to the Snowflake marketplace and request Kumo from there. Once you request, we should be able to share the app. I know someone said they haven't received a Kumo demo link. We'll definitely, get back to you if that's the case. But once you install the, you get the app, it would be shared to you and you can actually download. I won't go through the installation steps because it takes a while. But when you go through the installation steps, what'll go on is Snowflake will actually provision resources that you can completely run Kumo in your Snowflake. I have an installed version of the app, so I'm going to just go in and show you here what happens. So Kumo is installed, and we provisioned some GPUs and some compute. You've set up the connections, and all of this becomes really easy with the Snowpark container services. And once it's all set up, it's a few clicks of buttons. You can launch Kumo. And this is what Kumo looks like. We have both a UI and an SDK. And one of the core concepts of Kumo is a connector. So you would actually connect your data set using a connector. You would need to, in the case of the Snowflake, deployment, you would need to ask your Snowflake admin to share permissions with Kumo. It would look, they would write a script that looks something like this. So this works very well with your security teams. You would, potentially share your database, your schema, and potentially even all the views that you need to Kumo. You coming back to the Kumo app, we have a Snowflake connector. that you can, set up the warehouse, the database, the schema, and so on. I already have some connector set up, so we'll work with that. But once you have your, okay, I have, yeah, let's get back. Okay. We come to the next concept is the tables. And you can start connecting tables based on your connector. So let's say I want to bring in the articles table. We start looking at the tables and we will start doing an inspection here. We'll give this a moment to load. But we start inferring column types, and you can do some basic annotation on primary keys and actually start marking the date fields so we know which are the dates to index into the graph. Now, in this case, the primary key is the article ID. We can take large text, we can take images as well, but you can also bring in embeddings. And that's what I was trying to mention earlier. If you can call Cortex, you can call any other, AI platform that will give you embeddings, and you can bring in embeddings as well into Kumo. Then once you bring in the tables, right, and we have a simple H&M task that we're going with, you can bring in, you can say, I want to construct a graph. And this is really your primary key, foreign key. We try to, infer the links. Inferred are wrong, you can actually go change that. We can complete graph creation and we start writing those predictive queries. Let me show you. So what this looks like, right? So you come in, you can start typing predict. We have help and we have some autocomplete as well there. And we'll type in an example of our churn query. So here we have an example of the same churn query we saw before, and we bring in, as we type it up and complete it, the platform recognizes that this is a binary classification task. If we made a mistake, you can go back to the docs and always figure out what went wrong. And then you hit next. And here you can actually see advanced options that, if you want to go under the hood and start playing with the neural network parameters, you can start playing with it, right? So that's it. You've gotten to training a model. I think I saw this, it was 6 minutes ago when I entered the demo. You started training a model, right? How fast is that? Of course, it's a 3-table schema, but we have customers with much, much richer schemas. So what happens here is data starts getting ingested, a graph is created, and then we start running, neural network or, graph transformer search under the hood. Once your query runs, here's your output. So I did this a few days ago, and it took me about 10 minutes to run that churn query. It ran for two iterations, and then you can see your training metrics, you can see your evaluation metrics, things that you're used to in a standard ML platform. And the amazing thing, and a third innovation in Kumo is we've come up with explainability. So you can actually go down and see which features or which columns, right? Because we don't, the features are all, at the neural network layer, but which column in which table was relevant for this problem? And of course, the transaction count, because you're predicting churn, right? So the historical transaction is the most indicative. We have had so many users who use our platform and actually find data quality bugs by just observing this. We also have, individual instance level explainability that you can go in and inspect in the platform, right? And once you're all done, you can, come schedule batch predictions. We also have a notebook interface. So that's what this looks like. It's very similar, but some people prefer this. You again set up the connectors, the graph, you write a predictive query, and you can train a model. You can set the model planner config and so on. And the notebook interface definitely lets you play with, the output, because you can get the output of the prediction table and play around with it. You can also create, custom evaluation metrics that your business needs. So this is the demo, and let me come back to, the platform itself and talk a little bit about scale. Uh, we to summarize, Kumo lets you basically train ML models better, faster, and cheaper, right? And in Snowflake, what we're running under the hood, what you saw there is this, uh, I want to say, very complex, uh, high performant distributed system that runs GNNs at scale. We can scale to about 15 billion rows, 2,000 columns, and 2 terabytes of data on a per table basis. And to answer Chirag's question, at this point, we scale to up to 12 tables, and we can scale to bigger tables, but this has usually been sufficient for most of our customers. Kumo, in the Snowflake instance, actually works on, bringing efficiency and cost reduction for the data scientists. We leverage the best of the security, privacy, and scale features from Snowflake. And as for GNNs have been proven very effective in several places. In fact, LinkedIn started this work almost 7 years ago, and this year they won the KDD Best Paper in the ADS track. But it took them 7 years, and we estimate for all of these places it takes over $20 million or over in terms of investment to build. How easy is it to learn that predictive query? So initially when we created the language, creating a language is always interesting because you always wonder, how easy or hard is it going to be to learn? But we started doing these in spring. We do hackathons, we do workshops in companies. So if you're really interested in working, using Kumo, we can come and do a workshop with you. And usually we'll start with some open source data set. And this is from our spring hackathon, where we use the anime recommendation data set. And really by the second day, people were, writing a whole bunch of predictive queries. We had about 17 people who started and 12 people who stayed on till the end of that hackathon. And it was a 5-day hackathon. But over the time, they wrote 353 predictive queries. That's 353, models, but over 2,000 experiments, because each predictive query actually triggers multiple experiments. And what I love about this is we haven't worked on this data set. So, the yellow line here is a popular anime baseline. The red line is our data scientist just before the hackathon started and said, hey, I hope this is going to work. And he did a little better than anime, but with a very default query. And by the end of it, the 5 days, people had just completely beaten our internal team as well. Last few minutes, I'll actually talk about customers. We have customers across a variety of business. These include, ranking and recommendation like DoorDash, iFood, and others, ads prediction like Yieldmo, and then companies in the healthcare sector as well as retail. DoorDash is one of our flagship customers, and they've written about the work with GNNs for powering that try something new recommendations using Kumo as well. And they use our context GNN method, which basically, combines behavior that you see in recommender systems where someone, you want to predict based on past behavior, but you also want to you also want to recommend something novel. So we have our underlying architecture is called Context GNN, and we have a couple of publications up on archive regarding that, but that really helps the recommender use case. iFood uses us as well, similar use case. We forecast emergency room volume for one of our healthcare customers, and this is a forecasting problem. This is one where actually the customer brought in world knowledge. So it turns out that emergency room visits have some correlation to externalities, and external information was brought in this case as a table. This is an auto insurance customer. And in this case, the customer, uh, uh, they had one of the richest data sets in terms of number of tables. At some point, we were running, 30 plus tables for them. This is a much smaller view, and we were predicting bodily injury prediction. And within 8 days, 62, predictive queries were trained, and 51% improvement over the in-house model, right? And this was their life cycle. So this customer is really excited by Kumo that they, because each individual model would have taken 46 days for them. That was their internal calibration. And when they used Kumo, within 8 days, they got 60 plus models trained. These are the stories we see over and over and over again using Kumo. And we're hoping you would like to use us or work with us in many different ways. We're both hiring, but as well as, we hope that we can amplify your data science workflow in whatever you do. With that, I'll start taking questions. I'll take the next first one, which is so Chirag, I hope I answered your first question, which is the schema one. I'll go to the second one, which is curious, the team has thought through the predictive signals from GNN and feeding these node embeddings to an XGBoost model. Yes, super. We actually see this pattern not uncommon because many times, teams have some online serving mechanism through XGBoost or logistic regression already in place. Sometimes they want to combine, what you might see in the offline universe with some online signals as well. And yes, we have many customers who actually use us in the embedding way. I think some people have questions on the regular chat, so I will start answering some of those as well. Those of you who have not received a response or demo requests, you could also try just directly email hello@kumo.ai. I don't know if something went wrong when you actually sent the request. So thank you, Amir, for that. In terms of pricing, right now, our pricing is based on your data. We'd love to understand, Tesfa, from you what the consumption would be. So once you go through the workflow to request the demo, we can actually answer that. I've had another question, which is what's on the roadmap for the team? Question, I think many, many, many things. So I want to say from our notebook is product that we just showed is become generally available in, stay on the lookout for news for that. And then we really want to bring in additional capabilities that let data scientists do fast iteration on the notebook product. We're also, we also get a lot of requests around real-time serving and MLOps capabilities. So we're going to start baking some of that into our 2025 roadmap. Tesla, absolutely. Marketplace predictions with at that scale are definitely, that's our bread and butter recommender systems. and churn, lifetime value, things that you would actually want to do in a marketplace. So super excited to be able to talk to you. If not, I hope to see you all on demos or asking us to come to your companies and holding workshops. Tesfa, we also, like as part of our pricing plan, we can also throw some solutioning. Uh, we do offer data science, data scientists who would, help you onboard to Kumo. So it's not just a platform in the vacuum. You would also get advice on using the platform and becoming a GNN expert. I think that's our vision and passion. First question is if the persona is a backend developer. Actually, yes. So the idea of Kumo is you can operate at the predictive query level. We would always give you a data scientist to work with, but depending on how deep you want to go, you can go into the model planner, etc., etc. Nico asks if it makes sense for a company that doesn't have a fully developed data science team to consider working with us. I think that's exactly where we would like to, start working as well, is because data science really easy. So, when you either have zero data scientists or you have a few data scientists, that's when the data scientist has to just try so many things to find business impact. And Kumo doesn't need you to have an advanced DS degree. If you have an advanced DS degree, you can definitely, tweak the model further. But to start in Kumo, you do not need the advanced DS degree. So we cater to, multiple personas, engineers, data scientists, as well as business analysts within an organization.
If there's no further questions, this was an excellent presentation and clearly resonated with the audience. So I want to thank you very much for all of your insights and for giving us a great demo of this incredible technology. So thank you very much for everyone in the audience. If you'd like to rewatch this or if you missed any of it, it will be available at this same URL just a few minutes after the conclusion of this webinar. If you just refresh the page, it'll also be available on our YouTube channel tomorrow. So would definitely check that out and feel free to send it along. And then for those of you who are interested in demos or receiving more information about Kumo, we'll make sure that they have your information and can follow up with you. So thank you very much again, Hema, and everyone have a nice day. We'll see you next time.
Thank you so much. It was a pleasure.